Okay, so now we are going to talk about something can be viewed as something big in neural nets, which is called the convolutional neural network. So again, neural networks were reincarnated around 2010 with deep learning as the flashier name, largely a result of much faster and larger computing system. So remember, in 1990s, to train a simple neural net may take 3 days, but now it takes us like 15 seconds to do the same thing. Plus 1 or 2 new ideas. One important idea came up around 2000 was called convolutional architecture. Okay, so it works extremely well in figures or images recognition classifier. So it's the convolutional architect has 2 special types of layers, convolve and pool. So here I borrow or steal a figure from Efron and Hastie's textbook. So for our input, we will have several different hidden layers. We have one convolve layer here, another pool layer here, the second convolve layer here, the second pool layer here, another convolve layer here, and so on. So then I'll talk about so what it's all about. Let's go to our blackboard for a while. So let me erase something first. Okay. So remember, in our example, we have each image is a 20A by 20A matrix, and we can rewrite it as a 784 by 1 vector. Okay, so then our input we have 784 input. So intuitively, say if we have a 3-layer neural net, in the second layer or in the first hidden layer, we will first have a linear function which is W0K plus summation J from 1 to 784 WJK times our input J from 1 to 784, and we bring it into an activation function G, which in our example, which is the ReLU, or you may try sigmoid or hyperbolic tangent or any activation function you like. Intuitively, this is how neural net works. However, in image recognition, things are a little bit different. For example, let me first make some anyway. A mini, please. So what am I doing? Say we want our machine to recognize we have a 5 here and another 5 here. Those two may look a little bit different, okay, but they are also a little bit the same. If this is a 5, and we look at this square and this square, so you will see something in this square. You see something in this square. 你在2个方格中的同一个位置画一个小的方格，你会发现，如果这是5的话，在这个方格里面会有一画，在这个方格里会有一画。Another example will be we have 1 here and another 1 here. Okay, again, those 2 ones looks a little bit different, but there are something the same is if you look at this square and this square, So there's nothing here. What am I talking about? I'm talking about if you ask your computer to recognize, to classify image, the point is you can try to split your matrix into several squares. And look at this square and that square. If this is a 5, this square may be similar to this square. But if it's a 1, you have a 5 here and 1 here. If you look at the same location of this matrix, the square will look very different from this square. So basically what we are doing is we split our 28 by 28 matrix into several overlapping squares. Or let's go back to our slides. So we split our 28 by 28 image to 26 by 26 different response maps. Each response map is a 3 by 3 sub-image. Okay. Then, this is what we do. Let's go back to a blackboard again. So, what color do I have? Let me take. So, in this circle, let's say they are, I don't know. Let's call those elements belong to this square as L. So, in the convolve layer, what we are doing is our linear transformation can be written as plus the bias plus weights. But the weights is we only consider those elements in the response map. And put others 0. Put the weights of elements not in the response map as 0. The idea is when we want to do the image classification, we want our computer to look at one map by one map, one by one, maps by map. So at L2, the first convolve layer, original input is a 28 by 28 image. Our output is a 26 by 26 response map. Okay, so let's go back to our. So originally we have a 28 by 28 matrix. We may have one square here. It's a 3 by 3 square. Another square here. Another square here. Can be overlapping. Another square here. Another square here. So in total, we will have 26 by 26 smaller squares. Each of them stands for one neuron. And we don't stop here. We are not done yet. For each map, we give them several different neurons. In our example, for each response map, we give them 32 different neurons. So, in total, we have 26 times 26 times 32 neurons in this layer. So what's 26 times 26 times 32? Let's do it together. 26 times 26 times 32. So in this layer we have 21,632 neurons. And in each neuron, we have the special form of the transformation. We don't assign each input a non-zero weight. In each neuron, we only assign 9 of them non-zero weights. 9 of them belong to the same response map, non-zero with one bias. So in this layer, we have 21,632 neurons. In each neuron, we have 10 parameters. In this one single layer, we have 216,320 parameters. This is called convolve layer. So there are some jargons you may like to know. So first of all, this little square known as the response map, or somebody like to call it tensor. Okay, so this is for some one-dimensional vector is known as a vector. For some two-dimensional thing we know as matrix. If we have more than 3 dimensions, then it may be known as the tensors. Okay. Subfield are also known as the receptive fields, and those weights in the neurons are known as kernels or filters. They are just names. And the output are the sum of the element-wise multiplication of the receptive fields and filters, which means that the outputs are this guy. We take the summation of the weights times our inputs plus the bias. So the convolve layer is the spatial form of the neuron, which was tailor-made for image or figure classification, because in this kind of classification problem, we don't want to just look at one pixel by one pixel. We want to look at one region by another small region. So here is an example. Say we have a receptive field like this. Remember our input numbers between 0 and 255. When it's 0, it means left pixel is totally white. When it's 255, means this left pixel is totally black. When it's between 0 and 255, means it's gray, dark gray or light gray. And we standardize this guy, divided everything by 255, then we have something in between 0 and 1. So it's 0.039, which means it's light gray. When it's 0.7, means that's dark gray, 0 means white. Say our weight looks like this. Then the sum of multiplication is 0 times 0, 0 times minus 1, 0.353 times 0, plus 0 times minus 1, plus 0.039 times 5, plus 0.741 times minus 1, and so on. The thing is minus 0.545. Okay, and in this case, we transform our 28 by 28 input into a 26 by 26 times 32 tensor, or 32 different 26 by 26 response map. Okay. In this case, in the problem we are working on, this is good enough. Somebody are worried about it. Somebody say, but here, our response map is 26 by 26, smaller than the original 28 by 28 input. So somebody say, we should pad the borders, which means that, okay, in the originally we have a 28 by 28 matrix, which goes like, which goes like this. So in doing the convolve, we take the sub image. This is a sub image, This is another subimage. This is another subimage. So originally we have a 28 by 28 input. Then it will transfer into 26 by 26 different subimage. Somebody say, oh, I don't want the 26 by 26 subimages. Well, I want another 28 by 28 input. So the trick to do that is we pad the border. So we first amplify our original input. We write it, so we just copy the border here. So this guy is, intuitively, this guy can be the same as this guy. We just copy the border and do the same thing. But in this case, this can be considered as a subimage. Okay. This is called convol. Then another thing is called pool. The pool thing is, again, let's look at this example for the recommendation. Let me rewrite this in this 5 looks pretty bad. So we have a 5 here. So in the convolve layer, we may have several different overlapping image, sub-image like this. This is the image. This is another image. This is another image. This is another image. And after considering different overlapping sub-images, now we have a 26 by 26 map. And in this 26 by 26 map, let me write. I should pick a smaller number. So we can keep doing this, but this is the 26 by 26 matrix. We split into, we take this 4 as a group, 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 this 4 as another group. So we split this 26 by 26 matrix into a 13 by 13 matrix. And what's the value for each element in this matrix? We just pick the maximum of this 4. The maximum of this 4. Why not doing this? In this 26 by 26 image matrix, it represents 1, 2, 3, 4. These 4 overlapping subfields. In image classification, in image recognition, the point is, if we really care about if the computer see anything here. We don't care about, like in this part. We don't have anything here. So even if we take 4 sub-image here, and all 4 of them will report 0. We take the maximum of these 4, they are 0. But in this part, we really care about if computer sees something here. So we take the maximum out of these 4. We amplify the signal the computer sees. So this is the pro layer. At the L3, the first pro layer, the input was 26 by 26 by 32 tensor, and the output is 13 by 13 by 32 tensor. Each 26 by 26 response map can be represented as 13 by 13 non-overlapping 2 by 2 blocks. And for each block, we just take the maximum. So the pool operation reduces the size of image by a factor 2 in each dimension. Ideally, theoretically, to compensate, the number of tiles in the next convolution layer is typically increasing accordingly. So that is what we do. Let's go to our code, for example. So if you go down and down, you'll see this is the part I wrote for the convolutional neural networks, also known as the CNN, or CNN, or the CONVNET. So the first part is the reshape and transformation. Here we're doing a little bit different. When doing the convolutional neural networks, the Keras package asks the input to be a rank 4 tensor. So you have 4 elements. So the first 60,000 means that we have 60,000 different images. Each one is a 28 by 28 matrix, but the package asks us to have a 4-dimensional input. So the last element we just put 1 here. Technical issue. Again, the standardization, we divided everything by 255. So let's run this part. And this is our model. Okay, so first we say the first line here is the same as before. Model equals to models dot sequential, which means that we want to have a model and we want to input the model layer by layer. So it means the model dot sequential means that we'll put the first layer, the first hidden layer here, the second hidden layer is this guy, the third hidden layer is this guy. We just input it by hand, layer by layer, sequentially. So this is it. So first hidden layer we say want to split our 28 by 28 matrix into 26 by 26 overlapping 3 by 3 matrix. So here, this is, we say we want our sub-image to be 3 by 3. So we just put 3 by 3 here, and somebody like to use 2 by 2 or 5 by 5, for example. But most people will just use 3 by 3. And then we say we want to take the maximum of, we have a 26 by 26 matrix. We split into 13 by 13 blocks and want to take the maximum. So each block is a 2 by 2 matrix. This layer do it. This layer is called layers dot max pooling, 2-dimensional. And we do it again and again. But just in the next step, when I consider only 32 tiles, we consider 64 tiles. We do again, then we do the convolution again. Then in line 125, this is nothing but we were dealing with tensors or high-dimensional matrix. We say we transform the data back to a vector again, then bring it into our ordinary neural net, our ordinary hidden layer and ordinary submax. So we have 1 input layer, 1, 2, 3, 4, 5, 6, 7 hidden layer, and 1 final output. In total, we have 9 layers. And we can use the model dot summary. Model is the name we gave to this model, and model dot summary means I want to see some summary about the model. So this is our summary. So in the first hidden layer, we have 320 parameters. In each neuron, we have 10 parameters. We have 32 different. So we have 320. And here we take the maximum. And then in the second convolved layer, we have more than 18,000 parameters. We take the maximum again, no parameter. In the third convolved layer, we have more than 36,000 parameters. Then we flex the data, make them a vector again. Then we have another hidden layer. So in total, we have more than 93,000 parameters here. That is our model. Then we can try to train the model. First, we need the compile, which means we want our code, our Keras to report the accuracy, want the loss function to be the cross entropy, and want to use the RNSPROP as the optimizer. Then we can train the data. So again, we have only 5 epochs, and the batch size is not 128 now. Well, consider even smaller batch size, which is 64, and you'll find out that it takes a bit longer to train this model, longer than the simple feed-forward neural net we saw before. When I try it at home, it took me about 2 minutes, so we'll see how long it takes here. So each run, the first epoch, 28 seconds, so in total maybe a little bit more than 2 minutes. We'll go back to our slide, our results later. So here is what we do. So, any questions now? Yes, please. Good point. So you are asking why we consider 32. And earlier in our feed-forward neural net, we consider 512 neurons. So yeah, and our student just asked me in the break time why 512. So why we consider this number but not other number of neurons? So in my example, it seems to me I just arbitrarily suggest, okay, 512, okay, 32, okay, 64. So why we are doing this? So we'll go back to this very important question later, but yeah, let's take a look at the result first. So we can see, so it takes us a little bit longer to train this CNN. So for each epoch, it takes like 28, 27, 26, 27 seconds. But in total, okay, but now it's done. So in total, it took about 2.5 minutes. And our in-sample accuracy is 99.42%. So it's in-sample, but the in-sample error rate is around 0.58, so pretty good. And we can also take a look at the out of sample. So let's go back to this part. So again, we use the evaluate function to want to take a look at the out of sample test error rate. And the test error rate is, the test accuracy is 99.129, which means that the test error rate will be around 0.87%. Yeah, pretty good. So this is about the CNN. So as the student asked earlier, here I just arbitrarily say, okay, in the convolve layer, let's have 32 neurons. And in the feed-forward neural net, I just randomly said, let's have more than 500 neurons because I like 500 neurons. So is that the case? And intuitively, we should be able to select the number of neurons. So remember when we are doing the, let me erase this part on my blackboard. When we are doing the best function expansion, we have some model like this. We say our y equals to beta 1 plus beta 1 times b1 of x plus beta 2 to b2 of x, and so on, plus bp beta p times bp of xi plus some arrows, and those number p is something we want to select in the beginning. And if you remember what we talked about a month ago, yeah. So when we have a large p, intuitively we should be able to fit the unknown function better, so the bias should decrease. However, when we have a large p, the number of parameters we want to estimate is bigger, and we are worried about the overfitting. Anyway, the variance increase, and so on. So if the number of parameters decrease, the bias may be increased, but the variance may decrease. Okay, and in the neural net we have the same thing, which is if the number of neurons or the number of layers, if the number of neurons or number of layers increase, intuitively we can fit the unknown function better, so the bias will decrease, but we'll have a larger variance. It's the trade-off, no free lunch. So the key is we may want to have some balancing between the bias and variance. So we may want to have some, I don't want to say optimal, some good number of neurons and some good number of the layers. Conventionally, so if you want to have some more detail, Professor Kuan had a very good paper in 2008 talk about this. So in the last 2 or 3 pages talk about the selection of number of neurons and layers. We can do it by Bayesian information criteria. So we consider this model with 10 neurons. We feed the model, compute the Bayesian information criterion. This model has 20 neurons. We estimate the model and compute the Bayesian information criterion. We do it again and again. And in the end, we pick the one with the smallest BIC. Or, as you know, we can estimate the test error rate by the cross-validation. We should do that, right? And nowadays, people are also doing something different. So people say, okay, in the beginning, we want to have a big number of neurons and a big number of layers, and we put a penalty term here. Let's go back to our blackboard again. So let's say we have a large model here with a large P. One idea is we want to, from a different value of P, we can compute the Bayesian information criterion or any information criterion, model CP, or we can do the cross-validation and pick the best model. And if you remember, we call it the best subset approach. And another way to do that is, how about we just put every variable on the right-hand side, a large number of the inputs on the right-hand side, and put some penalty. The penalty may be a L2 function, and this penalty is known as the ridge regression. The penalty may be a L1 function, and this is known as the lasso regression. So in the neural net, we can do the same thing. Intuitively, we can add a penalty term. The penalty term may be the sum of the square of weight, which is nothing but ridge. But by the way, in the neural nets, they don't call it ridge. For some reason, they call it weight decay penalty. People like to call different names on the same thing. And nowadays, people also use the L1 penalty. Everyone calls it lasso. Nobody want to come up with another name. This is lasso. And we're not doing this in my example because two reasons. First, without doing any regularization, this model performed pretty good. So you may argue that it's not a reason. I'm just saying something I want to say. 我只是在耍赖而已。我只是随便选了一个数字，然后告诉大家说它表现得不错。But this is true. So it performs not bad. So we can do. The point is we can do regularization. I didn't do regularization here, and it performed pretty good. And so we may say if I do regularization here, it may perform even better. I just don't want to do that here. And another one reason I don't want to do that here is, it was in my blackboard, but I erased it. Remember, when we are doing the gradient descent, we have some loss function. We want to minimize this loss function to find the global optimum. But a neural net is a highly complicated, highly hierarchical model. Our loss function may be convex to the input, but it can never be convex for the weights. It can never be convex for the parameters. In other words, the loss function have many local optimals. And even if our model converge, we have no idea it's the global optimal or not. If you are sure you find the global optimal, then you can argue that, okay, now I have 10 neurons, I have 20 neurons, I have 500 neurons, 1,000 neurons, I have 5 layers, I have 10 layers. I can find the global optimal, each of them. I can compare them. When you are not sure if you can get the global optimal or not, what's the point? You have a model. You don't even know it's convergent or not. To argue about the model selection is, we don't know. So, yeah. 我不知道这个例子有没有这样，就是你想要选出一个最好的田径选手去参加奥运，然后我现在给你一群12岁小孩，然后你要做什么？你要做的是训练他们，训练到他们16岁、18岁，然后他们跑得够快了，就可以去参加奥运了。你不应该这样，还在12岁的时候挑选说，现在这样的12岁小孩，你跑得比他快，所以我要选你。他们才12岁，他们还有很多训练可以做，你不知道他们未来可以长成什么样子。我们现在在做 neural net 的时候，你更不知道你到了 global optimum 没有，你还有很多训练可以做。这个时候你去谈 model selection， 就好像太早了一点。我不知道我没有回答到你的问题。So back to our lecture. Here I show you guys some example. You may see here. Hey, in the first example, I put 512 neurons. In the second, here 32, here 64, here 64. Yeah, it's kind of arbitrary, if not random. So the only thing I can say that is first it works pretty good, and second although it works well, I'm not sure I got the global optimal or not. And so conclusion, I do not think we need to consider regularization issues seriously at this time. Okay, so finally, in this slide, I talk about some standard way to do regularization. Some people do. If you go back to 1990s, people did BIC. In around 2000, people did Ridge or Lasso. The very slide of this course. Nowadays, people are doing something called the dropout. What is the dropout? Remember, in our model, we have many different weights and many different neurons, many different weights, many different activations. Okay. For each layer, we randomly select several knots and drop them out. When I say drop them out, I mean that in this round of the computation, I set the values of those activations 0. So for each activations, we have a probability 5. 5 is some predetermined number, 0.5 or 0.3 for example. We have some predetermined probability 5, and with probability 5, those activations are set to be 0. And other activations which are not 0 are inflated by a factor 1 over 1 minus 5. For example, if 5 is 0.5, then this activation, it has a probability 1/2 to be 0. And another probability 1/2 to be double. So you may see what I'm doing here. It turns out mathematically, it can be shown that it is the same as Ridge. Okay, so and more importantly, by doing this, we are not adding any penalty term. We are not doing anything different from our algorithm. I just randomly pick some activation, set it to be 0, other to be double, and I train the model. It can be an easy way to do regularization. And that is our last slide for CNN and last slide for our course. Thank you very much.